Okay, we did example A in class. So that video is posted separately, and then your job is to make sure you understand the 3 following examples, and every part you don't understand, my recommendation is that you're writing down questions or highlighting it so that you can ask in class, because that's the purpose of this video. So we're going to go through the problems. Please pause if you need more time to copy or anything like that. Okay. All right, so the first thing that we're going to do is make the list of important information. So that includes our 3 asymptotes that we want information about: vertical, horizontal, or oblique, information about holes in the function, and information about the x-intercept and the y-intercept. So looking at this function, I see the numerator and denominator, and when I look for either a horizontal or oblique asymptote, remember there's one or the other because they emphasize end behavior. They're based on degree, like we studied the 3 different groups of the functions. So this numerator is actually of degree 2, because if I multiplied it out, if I multiplied out the numerator, it would say 3x squared minus 3x. So it's of degree 2. So is the denominator. They have the same degree, which means the function does go horizontal at its ends, which means it does not have an oblique asymptote. It has a horizontal asymptote. And this is the situation where we would use the lead coefficients to determine where that horizontal asymptote is. So this function's horizontal asymptote is at y equals 3/2. Before we go on to find anything else, we want to know if the function simplifies or not. So I'm going to actually factor the denominator since it's not in factored form. And so the denominator factors like this. Notice that none of the factors cancel. There's nothing removable from this equation. So for holes, there are none. Now I'm going to look at vertical asymptotes. Remember, that's when the function is undefined, and we would find when the function is undefined by setting the denominator equal to 0 and solving for x in those situations. So in this case, we have 2 vertical asymptotes at x equals -1/2 and at 3. For the x-intercept, we're going to set y equal to 0. And we're going to solve for x. Remember that we would do this by multiplying by the LCD, which in this case is the only denominator in the problem, on both sides of the equation. 2x plus 1 and x minus 3. And on the left side, we're always multiplying them times 0, so we're getting 0 equals this numerator. And here that gives us 2 different x values for x-intercepts. We get x equals 0 and x equals 3. So one x-intercept is at 0, 0, and another x-intercept is at 1, 0. For the y-intercept, we're going to set x equal to 0 and see what value we have for y. So when we do that, it looks like this. And we would get 0 in the numerator over -3 in the denominator, which is 0, and our y-intercept is 0, 0. Okay, so we're going to plot all this information on our graph. So we have an x-intercept of 0, 0, and 1, 0. We have a y-intercept of 0, 0. We have vertical asymptotes at x equals -1/2. And x equals 3, and no holes. So there's all the information on the graph, and now we want to analyze what's happening between them. So remember how this analysis works. I want to take my x-axis and the places that the function could end up going from above the x-axis to below or the other way around. So places it could cross over the x-axis, and that can either happen because an asymptote breaks apart the graph or because it literally crosses through the x-axis at an intercept. So here are the values I have. -1/2 is a vertical asymptote, 0 is an intercept, 1 is an intercept, and 3 is another vertical asymptote. So I have 1, 2, 3, 4, 5 different sections of graph that I need to test. And when I say test, I'm talking about testing them in this equation. And I'm kind of deciding, would the y values be negative or positive when I plug in different x values? So I'm first going to plug in an x value that's smaller than -1/2, say like -10. That would make this quantity negative and this quantity negative. It would make this quantity negative and this quantity negative. And overall, that would be a positive over a positive, which would turn out to be positive. Okay. Remember what that means for us? That means when we're sketching this graph, we only expect points above the x-axis for any x value that we plug in that is smaller than -1/2. And I actually forgot to mark my horizontal asymptote at 1.5, so I'm going to do that now. Sorry. And remember that that's there just for end behavior. So though I drew the whole thing, I'm really focused on the ends of that asymptote. Okay. All right, and now I'm going to go back and analyze a next value to plug in. So I need to plug in something between -1/2 and 0, so maybe -0.1. If I plug in -0.1, this is negative, this is negative, this is positive, and this is negative, which would give me a positive over a negative, which overall is negative, which tells me in my analysis that when I plug in x values between -0.5 and 0, I only get negative y values, and I can only draw in that portion of the graph. The next value I'm going to plug in is something between 0 and 1, so say 0.5. If I plug in 0.5, this factor would be positive, this factor would be negative, this factor would be positive, and this factor would be negative. I would have a negative divided by a negative, which overall is positive. And for my graph means that when I'm looking at the value x values between 0 and 1, they only produce positive y values, and I can only graph in there. The next section I'm looking at is between 1 and 3. So I'm going to pick to plug in a value of 2. If I plug in a value of 2 in my numerator, this first factor is positive. So is the second. In the denominator, I have a positive and a negative. So I would have a positive being divided by a negative, which overall is negative. And again, corresponds to me graphing. If I'm plugging in an x anywhere between 1 and 3, I expect only to have y values that are negative. And now I'm going to plug in a value greater than 3. When I plug in a value greater than 3, all of the factors in this expression are positive. A positive over a positive would give me a positive result, which means that I would expect my graph to be only positive y values after the x value of 3. So now I'm going to try and use this to sketch my graph. Remember what we know about behavior. We know that at the ends we want to follow the horizontal asymptote, and that as we approach vertical asymptotes, we either start to look very vertical as we get closer and closer to it, following it either upward or downward. So in this first section, this downward part right here would be impossible, because before that asymptote, I never got any y values that were negative, so I would definitely have to follow this asymptote more here, and this end behavior at 1.5 here. So I'm just drawing something that connects those behaviors. Okay. After the asymptote, again, I'm either very close to it going upward towards infinity or down towards negative infinity. And in this case, I'm going to go down towards negative infinity because there aren't any positive y values in this section of the graph. And I'm going to connect that behavior to my x-intercept right here. Okay. Then there's no asymptote. This x-intercept I just crossed through is going to get connected to this other x-intercept, and between them I expect y values above, so somehow it comes up here, but eventually turns around and comes back to that x-intercept. Okay. And then from that intercept I'm approaching another asymptote. So again, as we get closer and closer to these vertical asymptotes, our behavior either looks like it's going towards infinity or negative infinity. And so when I look at what's shaded here where I'm allowed to point, this would cross through so that the y values are negative and go towards negative infinity. The last section of the graph doesn't have any points or intercepts to connect. So again, I'm going to rely a lot on my end behavior here at 3/2. And remember, close to the asymptote, I'm either up towards infinity or down towards negative infinity. And in this case, I'm up towards infinity. And so I'm going to connect those two behaviors. And so that would be the best sketch that I have of this graph. Now we're going to look at one that has an oblique asymptote. Okay. So the way that I know that this problem has an oblique asymptote, if you look at it, is that the higher degree is in the numerator. And I'm going to think of this 3 plus x as x plus 3 just to make it a little bit easier. So as I list my characteristics for this one, I will write none next to horizontal asymptote, and I will go find an oblique asymptote instead. And we'll talk about how to do that. So oblique asymptotes are found using division. So you literally want to take the fraction and divide it. So I want to take 5x squared and divide it by x plus 3. I'm going to use synthetic division since I can in this case. I would be forced to use long division if I had to. I would put -3 in the box for synthetic division since I'm dividing by x plus 3. And my coefficients would be 5 because of 5x squared, and then 2 0 placeholders for x and for the constant. Then I would go through the synthetic division process. And what I have here is that this division problem is really the same thing as 5x minus 15 plus this remainder. So for your oblique asymptote, what we do is we use this answer, but we don't use the remainder. Because remember, oblique asymptotes are for end behavior, and ends of the function happen when you're plugging in really large numbers here. If you plug in a really large number for x, think about like 1,000,000, then this fraction is 45 divided by 1,000,003, which is a very, very, very small number. Which means at the ends of the function, you are almost exactly like this line, except for this very, very, very small number. So we are going to call it an asymptote, meaning we get very close to it without touching it. That accounts for this little extra number being added. But we have something that will guide us towards infinity or negative infinity. So 5x minus 15 will be our oblique asymptote equation. When I set the denominator equal to 0 in this equation, I would get x equals -3. No factors cancel, so there's no holes. For my x-intercept, I would set y equal to 0. And as I solve this equation, I would get x is equal to 0. So my x-intercept is at 0, 0. And if I plug in 0 for x to find my y-intercept, I will get 0 over 3, which is also 0, so my y-intercept is also at 0, 0. So I'm going to plot this stuff on the graph, so the intercept at 0, 0. And because of these values in my oblique asymptote, I'm actually going to label the the y-axis by 5s, but still label the x-axis by 1s. Okay, so my vertical asymptote of -3 is here. And then my 5x minus 15, that asymptote, this would be -15. And my slope would be up 5 over 1. So the line would go through these points. I'll draw it in just a minute. So this would be my oblique asymptote. Okay, and remember what the oblique asymptotes mean. It's all about ends. Where do the ends of the graph go? So this is really here to emphasize to me that the ends of the graph go towards infinity here on the right side and towards negative infinity here on the left side. And now I'm going to go through and do my analysis. So when I go to do this analysis for the x-axis, I have a vertical asymptote at -3 and an x-intercept at 0. So I have a lot less values to test. And remember, this is our equation that we're testing them in. As I plug in values to test, okay, so let's say I want to test a number in this section, something smaller than -3, like -10. -10 squared would be a big positive number times 5 would be positive, and -10 plus 3 would be negative, and overall that's negative. Okay? So that tells me on the left side of that asymptote, I can only plot points with negative y coordinates. Now I'm going to test something between -3 and 0, say like -2. I still get a positive in the numerator, but I also get a positive in the denominator, which overall is positive, and tells me that in between this asymptote and this intercept, all those x values plug in and give me positive y values, and I can only graph in that section. And then lastly, I'm going to plug in something bigger than 0, say like 10, and I get positives again in both places, which is also positive. So that tells me after that intercept at 0, all the y coordinates are also only positive, and I can only graph above the x-axis. So as I go to put things in, remember behavior. We want to follow the asymptote, the oblique asymptote at the end. And as we get close to a vertical asymptote, we either curve upwards and go towards infinity or downwards and go towards negative infinity. Based on my shading, the upwards is not an option here. I have to graph down here. So I'm going to graph something that follows this end going towards negative infinity of the oblique asymptote and the asymptote here. So maybe something like this. Then on the other side of the vertical asymptote, again, I either go towards negative infinity or infinity, and based on my analysis, it would be above the axis, so it'd be up here. And I need to connect that to this point I know exists on my graph. So I connect that to this point at 0. And that does not cross through the axis. Notice it stays up here, okay? And then the only other thing I know is I'm supposed to follow this oblique asymptote for this end behavior. So I would draw something that just becomes very close to that line and follows that behavior as it goes towards infinity. All right, the last example that we're going to do, oh, no, two more, sorry. Two more examples. So for this one, you're actually going to like that it simplifies. So again, I'm going to make my list of information. Let's see, holes and intercepts. So in this one, we have to be real careful because if we look at the factored form, notice that these cancel out right away. So what that should alert you to is there is something that gets removed from our equation, which means there is a hole. Now we want to figure out where the hole is at. So think about the simplified version. So first, think about what you canceled out. When would that have been equal to 0? At x equals -2. So the x coordinate of the hole is at -2. The y coordinate is whatever y value you get when you plug -2 into the new version of the equation. So in this case, it would be -4. So our hole is at -2, -4. And the way that we'll see that on our graph is we'll actually plot the point, but plot it open so that everyone's aware that it's skipped. All right. Now, I actually don't have a horizontal or an oblique asymptote in this situation because notice that it's no longer a fraction. This is actually just the equation of a line. What I'm now graphing is just y equals x minus 2. Okay? There's also no vertical asymptote because there's no denominator left. Okay? I can find the x-intercept. It's 2. So the x-intercept would be 2, 0. And I can find the y-intercept. It's -2, so the y-intercept would be 0, -2. So 0, -2. And 2, 0. And clearly, I made a plot wrong on my hole. I could tell there was something wrong in case you were having the same thing. How would I draw that line and that hole be part of the graph? I didn't actually plot it at -4, so let me fix that. -2, -4. And so you'll see this graph is just a line, because that's what it becomes when it's simplified, but it's a line that has a hole in it. Okay. So it's everything on that line except for that one point. So though this is a weird situation, you might like this because it has a lot less analysis going on than the other examples that we've seen. All right, the final example that we're going to graph looks like this. Okay. So again, I'm going to go ahead and rewrite the denominator in factored form. And notice that these factor out. So I am now going to really focus on this function. So really I'm focused on the equation 1 over x plus 3. But I do need to pay attention to the fact that I canceled something out, because remember, that means that we have wholes. Okay, so how do we figure out our whole? We look at what was removed from our equation was a factor of x minus 5. That factor would have been equal to 0 when x is 5. So my whole is at an x coordinate of 5. And then I need to know where that would exist on my new graph. So if I plugged 5 into the new equation, I would get 1/8. That's where my whole is. So 5, 1/8. 1, 2, 3, 4, 5, and just above the axis there. So for the rest of the information here, for my horizontal or oblique, notice the higher degree is in the denominator. That means no oblique asymptote, and that my horizontal asymptote is automatically at 0. For our vertical asymptotes, we determine when the denominator would be equal to 0, which in this case would be -3. You do not include this other factor. You already found that that's a whole. It cannot be a whole as well as a vertical asymptote unless you had multiple of those factors present in the equation. For my x-intercept, I'm going to set the equation equal to 0. So y is 0, and I'm going to go ahead and solve. Notice when I solve, I get that 0 is equal to 1. That's not true and doesn't solve for x. That means that has no solution, which means there's no x-intercept. And for my y-intercept, I will set x equal to 0, and I will get 1/3. So that means I have the point 0, 1/3 on the graph. So 0, 1/3. And then I'm going to fill in my asymptotes. So my horizontal asymptote is here at 0. Remember, that's really just there for your end behavior. I'm emphasizing the ends. Whereas your vertical asymptote is to split your graph apart into different branches. Okay. Now, when we look at our analysis here, we actually don't have a lot of different places to analyze. The only place our graph can cross over or change the y values is when it goes on each side of the asymptote that's at -3, because other than that, there's not an x-intercept that it can cross through. Guys, I must be having a bad day with my positives and negatives, because that was a y, 1/3, and I definitely did not put that in the right spot. So sorry, go back real quick and fix that. Okay, so we still just only have to analyze 2 spots because there's no x-intercept. So on the left side and on the right side of -3, and remember, I'm analyzing it in this simple version of the equation. So when I plug in a number over here that's smaller than -3, like -10, I have the one that's always positive over a negative, which overall is negative. When I plug in something that's bigger than -3, say like 0, I have a positive over a positive, which ends up being positive. Okay? And that analysis, remember, is telling me where I'm allowed to plot branches of the graph. And it's saying that on the left side of the axis, I should only plot points below the x-axis, and on the right side, only above. And so when I look at that, remember, end behavior, we really want to follow this on the left end, and it would have to be coming from slightly below that asymptote. And then as we get close to the vertical asymptote, I either start getting very vertical towards infinity or negative infinity, and in this case it would have to be negative infinity based on where my analysis says I can plot points. So I connect this end behavior to this behavior near the asymptote. On the other side of the asymptote, I have to analyze the behavior as well. Should I be going towards infinity or negative infinity? And you can see that I'm not allowed to plot points down here according to my analysis, so I should be using this behavior here. And I know I crossed through this graph and I have a hole here, and I'm supposed to follow this end behavior, but all above the x-axis. So I'm going to draw a curve that follows this behavior by the vertical asymptote, through the y-intercept, through the hole, but not really through the hole. Like I'm skipping it, but my curve still follows that and is basically following that horizontal asymptote. Okay. When you guys come back on Monday, we will go back through these graphs just to identify the domain and range, and we will specifically take questions that you guys have. So make sure you wrote down questions, highlighted things that were confusing, and start thinking about how you would label the domain and the range for these graphs.